Okay, so welcome everyone. Today we have a pleasure to host three young and promising researchers who will tell us about their thesis topics and the results they've obtained. So the first one is Tymon Frelik, who will talk about aspects of complex geometry and Cartan bundles in gauge theory. Tymon, the floor is yours.
Thank you, Bartosz. Okay, so in the next 10 minutes, I would like to summarize the general idea of the things I deal with in my master's thesis, entitled, as you said, Aspects of Complex Geometry and Cartan Bundles in Gauge Theory. It is supervised by Professor Javier de Lucas Araujo. So the motivating theme of my thesis is the Kempfness theorem, which is a theorem establishing a kind of correspondence between two notions of a quotient in symplectic geometry and algebraic geometry. Namely, that a quotient, a classical symplectic quotient of a Hamiltonian action of a compact Lie group G is equivalent to the geometric invariant theory, the so-called Git quotient of the action of the group G complexified in algebraic geometry under some assumptions on the manifold on which we are acting. Right? So these results have served as an inspiration for the study of certain kinds of systems of geometric PDEs, which may be formulated in terms of a level set constraint on the momentum map associated with the Hamiltonian action of an infinite dimensional Lie group, which acts on an infinite dimensional symplectic manifold. So these infinite dimensional manifolds frequently occur as spaces of sections of certain structures. So for instance, one can consider the space of connections in the vector bundle or a space of complex structures. And then one may endow it with a symplectic structure, consider the so-called gauge group acting on it, and stating certain partial differential equations for curvatures, for instance. One uses this Kempfness theorem as an inspiration to formulate some conjectures on obstructions and stability of solutions to these systems, right? So the original work that initiated this paradigm in differential geometry is Atiyah's and Bott's 1983 paper, Yang-Mills equations over Riemann surfaces, which is a very important and highly cited paper. As of today, it has almost 3,000 citations. And there are many other well-known problems in the similar spirit, such as the Donaldson-Uhlenbeck-Yau and Kobayashi-Hitchin correspondences, which are closely related, or the more recent Yau-Tian-Donaldson conjecture. So what is relevant to gauge theory here, if we remember that in kind of the geometric formulation of field theories, one usually considers a certain bundle over a manifold that classically is taken to be spacetime. In this paradigm, the equations for the compatibility of structures, such as, for instance, a Kähler metric and the Yang-Mills connection, somewhat resemble field equations in being also geometric PDEs. I will give a short example later. But the problem with this approach that already may have become apparent to you is that the original Kempfness theorem treats finite dimensional groups, while I was speaking of infinite dimensional problems on infinite dimensional manifolds. So in general, this passing from a finite dimensional to infinite dimensional framework is not always easy, since a lot of properties do not hold in infinite dimensions. Notably, many infinite dimensional groups do not admit complexifications, which is a big problem. Mm, so the diffeomorphism group is an example, right? We have a complexified algebra, right? So we can complexify vector fields, no problem. But if we want to integrate it to a group, there is an obstacle. Despite that, this Kempfness theory has served as an kind of an inspiration for infinite dimensional problems, but there has not yet been a rigorous generalization of the framework until a recent preprint by Diez, Futaki, and Ratiu entitled Cartan Geometry and Infinite Dimensional Kempfness Theory, which develops a new generalized framework for the Kempfness theorem, which easily generalizes to infinite dimensions by utilizing Cartan connections. So my master's thesis introduces complex geometry and Cartan connections in this context of gauge theory as a didactical tool for theoretical physics students. And we also discuss the framework of Diez, Futaki, and Ratiu and its relevant applications. So let me very quickly recall what a Cartan connection is. So we consider an H-principal fiber bundle of over a manifold M, which is endowed with a G-valued one form, which we call the Cartan connection, which satisfies three properties, that is equivariance with respect to H action, mapping fundamental vector fields into their generators in the algebra of H, and also establishing an isomorphism between a tangent space of the total space of our principal bundle at each point with the Lie algebra G. And given a Cartan connection, there is a natural notion of curvature, which is defined as such by the structure equations. And in considering Maurer-Cartan equations, which may be stated as a flatness of the curvature form, we see that indeed a quotient projection from G to G over H, a Klein geometry, is a flat Cartan geometry. So this is a quick recap of Cartan connections. Let us now introduce the fundamental definition in the work of Diez, Futaki, and Ratiu. We consider a manifold M and a Lie group G which acts on it. Next we consider a Cartan geometry of type AG, right? So G is the algebra of our group, which we will call an orbit through a point M if the following two conditions are satisfied. Firstly, there is a smooth G equivariant map chi from the total space of our Cartan geometry to M, such that the point M in M is in the image of chi. And next, that we have a Lie subalgebra AM of A, and a right Lie algebra action on P, the total space, denoted here alluding to fundamental vector fields for any element of AM and any point in the total space, which commutes with the G action and such that the property of annihilation of the tangent map of chi by the fundamental vector field holds. This Cartan model, which defines an orbit through M, defines a fiber-wise linear map, which gives an analog of infinitesimal action, like here. So this is defined with respect to the inverse or the dual to the Cartan connections on our orbit. And so by abuse of notation and establishing this correspondence with infinitesimal action, one is free to write that indeed there is an action of a Lie algebra element on chi of P, which is a point in M, in the manifold M. Right, so let us give a very, very simple example of this construction, the most minimal one. So we consider a Lie group A, which acts on the manifold M. Then we consider its principal Lie subgroup G. Principal means that A over G or quotiented by G is a manifold, and we have a natural principal G bundle structure. So this is obviously always satisfied in finite dimensions, but it's not always the case in infinite dimensions. Okay, and on A to A over G, which is our principal G bundle, we have a Maurer Cartan form, which defines a Cartan connection. And it is a Cartan model for an A orbit through any point M on our manifold. So the map chi, the equivariant map is simply given by the action of A on any point of M, and then kind of justifying the terminology for the AM Lie subalgebra. We have AM as the Lie algebra of the stabilizer subgroup of the point M, which acts on A by right translations. So the infinitesimal action map is given unsurprisingly like so. And then we want to introduce how this framework generalizes complexifications, right? So we consider an action of the complexified group on a symplectic manifold, and we want to generalize it. So let us first recall that a Lie algebra action of the Lie algebra G on a manifold M, which we endow with an almost complex structure that is an anti-involutive endomorphism of the tangent bundle, extends to an IJ complex linear map given as such, right? So we have that I is the complex structure in the vector space, complex vector space GC, right? Which is a complexified algebra. And then in terms of infinitesimal action of the Lie algebra on the manifold, we have the complex structure given by our almost complex structure on the manifold for any two elements in the algebra. So we consider the manifold M group G acting on it and an almost complex structure as before. And we will call a Cartan geometry of type AG a model for the complex orbit through a point M in the manifold M. If firstly it is an orbit, as before, through M, and we have the following equality. Namely, the image or the range of the tangent map of chi at point P in the total space P of our Cartan geometry is equal to the image of the IJ complex linear map, which comes from complexified Lie algebra action. So the merit of this generalization is that the algebra A may be strictly smaller than complexified Lie algebra GC, and in fact, it may not even be a complex vector space at all, right? So the important property that we're taking note of here is simply that our action on M results in the same distribution as the complexified action would, right? So this is a subtle point of the theory. And in terms of applications to gauge theory, I will quickly outline how it treats the Hermitian-Yang-Mills equations problem. So we consider a smooth complex vector bundle over a compact Kähler manifold, which is given by the data of a manifold, a symplectic form, and a compatible complex structure. So we fix a Hermitian metric H0 in the bundle E, and we consider the unitary gauge group of automorphisms of E that preserve the Hermitian metric, right? So since we are considering automorphisms of the whole bundle, this is an infinite dimensional group. Next, let us denote by A of H0 the infinite dimensional space of H0 unitary connections in E, such that the associated curvature is a 1-1 form, right, with respect to the holomorphic bigrading of forms on an almost complex manifold. So the 0-2, which is the fully anti-holomorphic part of the curvature, is vanishing. And it is seen that A defines a holomorphic structure in E. So the gauge group acts on that space of connections by inner automorphisms, right? dA denotes the exterior covariant derivative. So we are free to consider the complexification of this action, which is not problematic since this time actually the complexified algebra does integrate to the complexified gauge group, which is not always the case, as we have said. For the Cartan bundle associated with this action on E, we can simply take the natural quotient bundle as such, and the Morer-Cartan form on the complex gauge group defines a flat Cartan connection. We have the natural modeling map, and here are the Hermitian-Yang-Mills equations, which state this kind of proportionality of curvature wedged with the n minus first exterior power of the symplectic form. Using the framework of Diez, Ratiu, and Futaki, we can restate this problem rigorously. And there is the notion of the so-called generalized Futaki invariant, which yields the abstraction to the existence of solutions, and that is connections which solve this equation. So I'd like to say this in more detail, but I'm constrained by time, which I've already used up. So I'll just give the references, the first one being the original paper by Diez, Futaki, and Ratiu that I'm referring to. Then we have the Attia Bot paper. These two papers refer to or actually all four of these papers refer to the problem of Kobayashi-Hitchin correspondence and Donaldson-Uhlenbeck-Yau problems. Thank you very much.
Thank you very much. Are there any questions? Okay, if not, I have one. You mentioned something as Futaki invariant. Could you shortly tell us what it is and in what sense it is invariant?
So it is an Futaki invariant. Originally, is motivated. It is a Lie algebra character on the infinite dimensional space of holomorphic vector fields, and it is originally motivated by a simple observation that I think is due to Bourguignon, that if you have a one form on a manifold, that's firstly it's closed and then it's invariant with respect to action of the group G, uh, then if you evaluate this one form on a fundamental vector field corresponding to that group action, then this evaluation is constant, right? And so one may form a functional using this invariant. So there are many invariants that one could form this way, one of them being the Futaki invariant, and one may then consider a certain functional that's defined by the Futaki invariant, and it turns out that this functional, the vanishing of it gives the obstructions to the existence of solutions for many problems. That's kind of a very rough intuition.
Okay, so to construct this invariant, you need to momentum map,
Yes.
as far as I understood.
Yes,
So, and you also said that the invariance is with respect to the group action. So I guess the momentum map also has to be some kind of invariant or
equivariant. Yes,
equivariant. Yeah.
Yes. There is.
Okay. And could you comment it on the ad equivariance in infinite dimensional manifolds case?
Well, it's not straightforward as well. I would probably be more comfortable referring to the paper by Diez, Futaki, and Ratiu. They have a good in this paper, and I think one of the earlier papers by Ratiu and Diez, they have a good intuition for how to treat this in infinite dimensions. In any case, better than I could summarize here and now.
Okay. Thank you very much.
Thank you.
Are there any more questions or remarks? Okay, so maybe one more question. Since it's in a infinite dimensional setting, and from my experience, for instance, doing Poisson geometry and infinite dimensional setting is much more complicated than in a finite one. So could you comment on some difficulties that appear?
Right. So there are many things which do not generalize to infinite dimensions.
Yeah, that's right.
Kind of the most immediate one, as I said, is that we don't have, I think it's called Lie theorem, right? That we can, under certain mild topological assumptions, that we can integrate a Lie algebra into a Lie group, which is this is kind of the main obstacle that this paper deals with, right? So this is why we have to introduce Cartan bundles to get around this problem. And there are many formal subtleties in formulating other usual structures. So that's why you will see a lot of kind of functional analysis popping up